Welcome back to week 11 of Bio 6612. In this final lecture, we're going to talk about inference for mixed effects models. We're going to briefly cover best linear unbiased predictors and restricted maximum likelihood estimates. And then we're going to go into practical ways of getting inference for random effects models, including p-values and confidence intervals, as well as a couple model diagnostic plots and some model comparison. And I've added a couple links here if you want to deeper dive into any of the issues that I'm going to be talking about in this lecture. So very briefly, I want to mention restricted maximum likelihood estimation. I'm not going to go into any of the details of what this actually is, but I think you should be familiar with the term and that it exists. So in earlier parts of this semester, we talked about using maximum likelihood estimation, and we calculated maximum likelihood estimates in some cases. An alternative that is often used in mixed effects modeling is what's called restricted maximum likelihood estimation, or REML. And this is what's often used to fit linear mixed models. And when I say fit the model, what I mean is this is a way to estimate the parameters, like the fixed effects and the random effects, in linear mixed models. And I'm talking in particular about the fixed effects here, the fixed effect parameters, as well as the variances. And so you can use REML or ML for this estimation, but restricted maximum likelihood estimation is actually the preferred approach. And that's because in linear mixed models, the ML estimators are actually, of the variance, are actually biased. And this is particularly true for small sample sizes. As sample size increases, that bias decreases. But because of this bias, REML is the default method for fitting LMMs using the LME4 package. Because these estimators are unbiased. However, the way these models are fit means that you can't compare. If you fit using REML, you can't compare using different models with different fixed effects. So if you want to compare models with different fixed effects to each other, then you're going to need to fit those models using maximum likelihood estimator. And you can actually specify whether you want to use maximum likelihood estimation or restricted in the LMER function. The second thing about estimation that I think that is important to know about, but I'm not going to go into detail with, is what are called BLUPs, and these are the best linear unbiased predictors. That's what that stands for. And this is how we estimate the actual values of the random effects in linear mixed models. So the random effects themselves are the best linear unbiased predictors of those terms. And this is this is just a specific way of calculating those effects. I'm not going to go into the details of how, but it's good to know that there's some theory behind it and what they're called. And what BLUPs do is they shrink the random effects estimates towards the population mean, which means that, say you have some random intercept model where you have a population mean but you also have, say, some subject up here, and that's their that purple line is their own fit. What the BLUPs do is they shrink this person-specific fit towards the population mean. So that fit is going to be constructed using information about the subject-specific measurements, as well as measurements across the rest of the population. And where this can be particularly useful is for data that's imbalanced when you have subjects with not that many data points. If they don't have that many data points, their estimate for the random effect is going to be shrunk closer to the mean because there's more information there than there is for that individual subject. So that's all I'm going to talk about in terms of theory, but it's good to know about those two different methods of estimation for models, and definitely ask me questions if you're interested in knowing more. But I'm going to go into actual inference for the models that we've learned about now. So the first thing that you might be interested in doing is testing single fixed effects in your models. And what I'm talking about when I say testing fixed effects, I'm talking about getting p-values and confidence intervals for things like the betas. So, and there are various different approaches one could take for getting inference in mixed effects models, but not all of them are actually going to be good. So you could, in principle, do a walled z-test because you're using a likelihood. However, this is not advised because they're inaccurate in many scenarios, so it's not even provided by the LME4 output as an option. Another option is t-tests, and LME4 does provide a t-statistic. However, these are going to be best for balanced data, and they require you to calculate the degrees of freedom for the t-distribution you're using based on the number of parameters in the model, which is not actually always trivial because due to the way that the random effects are calculated, figuring out the degrees of freedom can be complicated. Other option is likelihood ratio tests, and finally the best option, one that will work in every scenario. And when I say it doesn't work in some scenarios, I mean that when you have data that's particularly imbalanced or a particularly complicated model, the inference might be more difficult to come by. But it will always work in the case of the bootstrap, so that's probably the best approach. However, I'm going to give you a couple alternative approaches as well. So why doesn't LME4 return p-values? Well, I added some links at the beginning of this lecture if you want to read up on it more. But the main reason is that they don't want you to misuse the results and assume that those are accurate in all different models that you might run. Because really, only the results calculated using the t-statistic are going to be accurate under some scenarios, and that's because it's hard to calculate degrees of freedom for comparing the t-distribution of interest under the null hypothesis. In simple cases, meaning balanced studies where you only have a few random effects, it's not that hard, and that's really the kind of cases that we're looking at in this class. However, in other cases, it can be quite complicated. And so there's actually a whole conversation around the best way to calculate p-values in linear mixed effects models. Other statistical programs like SAS and SPSS kind of just give you a p-value, and so you don't have to think about this as much. However, each program seems to use a different approach in how they actually calculate those p-values, so you don't necessarily get the same results from one program to another. So it is good to be aware of this issue. So some approaches that you can take to get inference is to approximate the degrees of freedom in your model. And there are two main ways to do this. One is called the Satterthwaite approximation, which is implemented in what's called the LMER test package. And I like this package because it's easy to use, but it works best when you have relatively balanced data. Doesn't have to be perfectly balanced, and simple effects. So like a single random effect, or maybe a random slope and a random intercept would be generally pretty safe here. Then the Kenward-Roger approximation is somewhat more reliable, but can be computationally expensive for large data sets. And this is implemented in the PBKR test package, and you can also use it in the LMER test package. And then another way to get inference for fixed effects is to bootstrap confidence intervals and p-values like you learned in 6611. So to talk about inference, we're going to go back to that student GPA data set from the previous lecture. I say lecture 11.4 here, but what I mean is lecture 11.3. So I'll start out with a model of a random intercept model that looks at GPA over time, controlling for sex and job status. So the variables are GPA, which is the outcome, occasion, which is the time variable. There are 6 time points per subject, each one measurement at each of 6 different semesters for each student. The sex variable, which is binary, and then job, which is the 3-level categorical variable. So first thing I'm going to do is run the model the way that we did last time. So I'm loading the LME4 package, and then I'm loading the data set from the website, and finally I'm running the model by calling LME4. I'm defining my fixed effects here for time, sex, and job status, as well as my random effect, which in this case is just an intercept. And looking at the summary of that, the output that's returned, once again, you can see you don't have p-values given here. You have a t-statistic, but you don't have p-values. But you do have your estimates. You have your fixed effect estimates, but you just don't have any inference for those. And again, job was a 3-level categorical variable. So we have 2 betas for that one, because you have in here the reference category, I think, is working for 1 hour a week or something like that. So instead, what you could do is if you load the LMER test package and refit the model, you will then get p-values. And these p-values are calculated using a t-test for each parameter, where the Satterthwaite approximation is used to calculate the degrees of freedom so that you can get that p-value. Otherwise, though, the model is fit exactly the same way, because the way that the LMER test package works is they take the same LMER function and they return a couple other things that would be needed in order to calculate that p-value. But the way that you actually call the LMER model looks exactly the same as we did in the previous slide using LME4. However, the order in which you load the packages is going to matter. If you want the p-values, you have to load LMER test package after you load LMER4. Or you can call specifically the LMER function associated with the LMER test package by calling by using this particular syntax. So if we look at the coefficients table from that summary, now we can see there's a column for p-values where there wasn't before. And those are the ones calculated by LMER test. And we can actually see in this model that all the fixed effects are statistically significant. So when you use LMER test, you can also use ANOVA to test one or multiple variables using a likelihood ratio type test instead of a t-test. If you use, and as a side note, if you use ANOVA called on the model from just LMER without loading LMER test, you're not going to get a p-value. However, if you use the ANOVA with LMER test, then you do get a p-value. And it's actually based on an F test rather than a likelihood ratio test. And you can specify using either Satterthwaite's or Kenward-Rogers method for calculating the degrees of freedom. And calling that model here, I call ANOVA. I give it the name of the random effects model. It's calling the LMER test version of ANOVA because I loaded that package later. And this DDF argument is where I'm defining how I want the degrees of freedom to be calculated. The Satterthwaite is the default, so that will be used automatically. However, if I use DDF equals Kenward-Rogers, then I will get the Kenward-Rogers method. And so what I get here I was just using the random intercept model. So what it's going to do is it's going to give me a p-value for each of the different covariates that were added to that model. So the 2 levels for job plus the sex and occasion. And this also is telling us that we have significant p-values. And as a side note, in this particular case, this is a fairly simple model with balanced data. And the degrees of freedom calculation gave the same number of degrees of freedom for Satterthwaite or Kenwood Rogers. They gave us exactly the same results in this particular case. I ran both of those models. So that actually gave us a test for the job variable, all three levels of it at once. However, you can explicitly test for multiple variables or multiple coefficients simultaneously using ANOVA the same way you have for linear modeling type situations. However, when you do that, when you compare two models with different fixed effects in the linear mixed model framework, you're going to want to refit the model using maximum likelihood instead of restricted maximum likelihood, which I alluded to in the slide before. And that's going to actually be done for you explicitly when you call ANOVA on two separate models. So what I'm doing here is I'm defining a reduced model, which is the same as the previous random intercept model, but now I don't have a fixed effect for job anymore. So that's why it's the reduced model. I can run my ANOVA with the reduced model and that random intercept model. You're going to get a warning message that tells you that the model is being refit using maximum likelihood instead of restricted maximum likelihood. And then you'll get your results printed here. In this case, you see that or significantly, the p-value indicates that adding that job variable gives you statistically significant results, much the same way that we've seen in other likelihood ratio type models. Okay, so those both give us ways of getting inference on our fixed effects. What about diagnostic plots for your model, making sure that it's a model that you actually like? So a couple things to keep in mind when you're trying to evaluate your model are, one is that the residuals should be normally distributed and homoscedastic. And two is that the random effects should be normally distributed as well. So generally I make two plots associated with that to check these assumptions. Checking that the residuals are normally distributed and homoscedastic means that over time, or whatever other variable that I am considering putting the random effects on, the residuals should be roughly around 0, and they also should be about the same at each of the different time points, have about the same variance. And in this case, I have higher variance at some points, like the first couple, than I do at some of the later time points. So it's not too bad, but there's some evidence here that we might not have homoscedasticity. So I might want to consider adding other random effects to this model. Another thing that I always like to check is that the random effects are normally distributed, because this is another assumption that's being made in this model, and you can do that by extracting the random effects and plotting them. So here I've plotted the values of all of the random intercepts as a histogram. So the way that you actually extract those random effects is using the ranf function around the name of your model itself, and then you'll have to sort of do a little bit of weird indexing to extract those numbers and put them in a data frame. But here I'm putting the random intercepts into a data frame and plotting them as a histogram using ggplot. And you can see here that the random effects are scattered around 0, which is what you would want to see. And the reason that you want to see that is for your random intercept, you start with your population level parameter, and all the other intercepts are going to be scattered around that beta 0 value. So that each individual's intercept is actually beta 0 plus their own beta I. So beta I is going to be scattered around 0. And here it does look like the random intercepts are roughly normally distributed, which is good. If we saw that those were not normally distributed or very skewed, it might be an indication that that random intercept is not useful for that particular set of data. So I also want to briefly touch on using AIC for model comparison. So we've looked at AIC in previous types of models to compare between different models, and we can use this for both nested and non-nested models. And the AIC is based on the likelihood, the data likelihood given the data. As well, and so it is generally safe to compare random effects models using the AIC. And in the same, we have the same interpretation as we did before, where a lower AIC indicates a better model. However, you can really only make this comparison when the models are fit using ML rather than restricted maximum likelihood. So if you do want to compare models using AIC, you need to make sure that you're fitting the model using maximum likelihood. And the way that you would do that is the same. You run the model the same way that you would normally, but then you have this extra argument called REML equals false. So the default is REML equals true. So meaning that the default is to fit using restricted maximum likelihood. But when you refit, you can fit the model instead using REML equals false, and that will fit your model using maximum likelihood instead of restricted maximum likelihood. And this can actually be useful for comparing models with different random effects. Sorry, I want to clarify something for a second here. So you need to do that, or you need to refit using maximum likelihood if you're comparing models with different fixed effects but the same random effects. However, if you're comparing models with the same fixed effects but different random effects, say they have the same fixed effects but one has a random slope and one has a random intercept, then they can be calculated using restricted maximum likelihood or maximum likelihood. It doesn't matter as much in this context. And so I have some code below where I defined a random slope model on that data that we were looking at before. And I use the AIC of the random intercept model and the random slope model to compare. And in this case, it indicates to us that the AIC is quite a bit lower for the random slope model. So that might be a better model for this particular data set. So something that's worth considering, adding a random slope. So it can be a little bit confusing when you are building a random effects model on how many random effects you want to include. And it can be more of an art than a science. However, there are a couple things to consider that can help you choose between different random effects. One is to compare models via the AIC like we did in the previous slide. Another is just to plot the data. EDA can help with this as well. And plotting the random effects. And a final way is you can do significance tests of random effects that involve bootstrapping the sampling distribution. And I'm not going to go into the details of how this actually works or what distribution we're bootstrapping. However, there's a nice package called RLRSim, which provides an exact likelihood ratio test using bootstrapping to test the significance of random effects. And this package can be slow and tricky to use for testing random effects in complex models. And it also only works for LMMs defined using the LMER function. but it can be really nice for getting mixed effects model, for getting p-values of your random effects in simple settings like the ones that we've talked about. And the way that it works is you have to load the library, and you build a LMER model the same way that we already did. And so I'm actually just going to call that same random intercept model. I'm also defining a model here without the random intercept. So this is the same model, same fixed effects, and I'm using LM because I don't need any random effects here. Same fixed effects as I had for this random intercept model, just no random intercept. And I'm using this exact LRT function to compare that random intercept model to the model without any random effects. And I get a small p-value here, which would reject the null hypothesis that those models are the same, and I would conclude that the random intercepts are a good addition to the model. And that's it for inference. We'll go over some more examples in lab in the next couple weeks.